Welcome to another lecture for the UBC course ISCI 344 Game Theory. Today we'll be talking about multiplayer games. My name is Rick, and my co-teacher, who originally prepared these notes, is Christoph. So let's get a quick overview of what we're going to do today. The multiplayer game that we're going to focus on is called the public goods game. The lessons we learn from it should apply to other games, but it's a particularly interesting one to study. We'll approach it using our economic solution concepts, and in doing so we'll see that there's a conflict of interest or a dilemma, and then we'll approach it using an evolutionary approach. And this is an interesting case because it highlights a common theme in evolution, which is the problem of cooperation. The problem there being, how do we how does cooperation emerge and sustain in an evolving population? Okay, so the public goods game. The idea here with this and other multiplayer games, and when I say multiplayer, I mean more than two players. So there are group interactions, and we fix the size of the group. Let's say there are n individuals, players in the group. So this is just one example of a multiplayer game, and the way we'll set this one up, we'll kind of make it clear why it's called the public goods game. So in this game, there are two possible strategies. There are cooperators, and we'll denote that strategy by C sometimes. They pay a cost, and let's call that little c, in order to contribute to a common good or a public good. The other strategy is to defect, call that big D, and they contribute nothing. Now in this game, there are three stages, and let me represent them with a little picture. So the first stage is the contribution stage. And the idea here is that we have our n individuals. Let's say we have, let me make this guy red. So what I'm imagining here is that blue guys are cooperators and the red guys are defectors. And there's a common, let's say it's a pot of money that people can contribute to. Okay, so the two cooperators contribute a cost C into the pot. That's the first stage. The second stage is a growth stage. And what happens there, the money in the pot grows. So maybe we can imagine that the whole pot grows. And the way the growth works is we say the money in the pot is multiplied by a factor of R. So in this case, I've doubled it, so R equals 2. And the third stage is distribution. And the total amount in the pot is distributed equally to all of the players, regardless of whether they were cooperators or defectors. So the essence of the game is that only cooperators contribute. The amount that's contributed is grown by a factor of R, and then that total amount is distributed to everybody. And in this example, we have 4 players, n equals 4 in the game, and the multiplication factor, the growth factor, is 2. And what makes this a public goods game? The investment, that's the amount that's resulted after the growth stage, it's a public good. So it's shared equally among all the players. So let's figure out what players should do in this game. That's a dangerous way of saying things. I shouldn't say should. What I really mean is what rational agents will be likely to do. Should implies it's a moral, prescriptive solution. So how can we think about this? The easiest way to think about it is to say, okay, if I'm in a group and there are, let's say, K other cooperators in the group, what should I do? And I'll put should in quotes there, just so we remember that's just, we're trying to describe what rational players do, not prescribe what they should do. So how can we figure this out? A rational player would simply choose the behavior that maximizes their expected utility. So all we need to do is figure out the payoffs, or the utilities, for playing each strategy, and figure out which one is bigger. So if I choose the defect strategy, then my payoff, let's write it as P sub D in the presence of K other cooperators. Well, how many people contributed any amount? K of them did. They each contributed a cost C, so that's how much was put into the pot. That is multiplied by the factor r, and then that's shared equally between everyone. So my share is 1/nth of the total. What if I cooperate? Then my payoff as a cooperator with k other cooperators. How many cooperators in total are there? Now there's the k other ones plus me. We each put in a cost c, so there's a total in the pot. It gets multiplied by r, shared between everybody. But don't forget that because I put in a cost C, I'm down C dollars or whatever units this is. So we can compare these two things pretty easily, because you should see that the payoff for the cooperator is equal to the payoff for the defector with the same number of cooperators minus some amount. And that amount turns out to be 1 minus R over N times C. As we discussed before, the rational thing to do is to choose the higher payoff. So which payoff is higher depends on how big R is. If R is less than N, the size of the group, then the second term here, this term as a whole is negative. So that means PC is going to be less than PD. PC is less than PD. So PD is more than PC, which means the rational thing to do is always defect. Now notice that doesn't depend on the size of the group or on the number of other cooperators. Okay, the other case is if R is bigger than N, then things turn around. Then this whole term becomes positive, and PC is bigger than PD. So the rational thing to do then is always cooperate. Okay, that's all cool, but that kind of thinking may have surprised you a little bit, because we've been pushing these solution concepts like the Nash equilibrium for so long in this class. So can we figure out what the Nash equilibrium is? The problem is we can't write down a payoff matrix because it's not a two-player game. So there isn't just a row player and a column player. Now there are n players, and n could be, 3 or 3 million. So if you wanted to write that down, you'd need n dimensions for your so-called matrix. But nevertheless, we can figure out what the Nash equilibrium is just by remembering something about dominance. What we're seeing here is that there's one strategy, either defect or cooperate, that dominates for any k. If R is less than n, then that strategy is defect, and if R is bigger than n, that strategy is cooperate, which means the other strategy can be eliminated. And remember, when we're applying elimination of dominated strategies, it will never remove a Nash equilibrium, as long as we're talking about strict dominance, which we are here. So basically, for every player, the dominated strategy is eliminated, leaving only one strategy. And the final outcome then is that they must all play that one strategy, and that must be the Nash equilibrium. So let's lay those out. If R is less than N, then everyone playing defect is the Nash equilibrium. On the other hand, if R is bigger than N, then everyone playing C is the Nash equilibrium. Let's just have a quick look at the payoffs under these special cases when everybody is playing either defect or cooperator. Our motivation for doing this is we want to see if there's any kind of social dilemma, but working out the Pareto optimum, or optima in this case, is really difficult. Actually, I'm not sure if it can be done. So instead, what we can just do is compare these limiting cases and see if the Nash equilibrium is also the mutually preferred outcome. So the payoff for each player, if everybody is playing C, cooperate, is the payoff if there are n-1 cooperators and I am also a cooperator. And from up here, we see that if we plug n-1 in here, then we just get an n up top, which will cancel with this n, and things will simplify. So these n's will cancel out, and we just get C times R-1. Okay, for comparison, what if everybody is a defector? This one is a little bit easier to figure out, because if nobody puts any money in the pot, then there's no money in the pot. But we can also work it through. If there are 0 other cooperators and I choose to be a defector, then we have the formula right here. And the important part is that k is equal to 0. So we get 0. So what have we learned? We've learned that always cooperate is better than always, or everybody cooperate is better than everybody defecting if R is bigger than 1. And R is bigger than 1 isn't a really hard criterion, because if we're playing a game like we have in this picture, you can see that it would be kind of a silly thing to put your money into the pot if it's going to depreciate, if you're going to lose money by doing that. Then, maybe you should just hold on to it instead. So that means that in the case that R is less than N, or technically 1 is less than R and R is less than N, in that range, then we have a social dilemma, because the Nash equilibrium is not mutually preferred. The players would like to agree on another outcome, but because of their own self-interest, it's a difficult thing to do. Each one of them will be tempted to defect from the strategy, the mutual all cooperate strategy. Oh, I see, I left out a word here. There's a social dilemma, let's say, for the case 1 is less than r is less than n. Okay, now let's switch and talk about evolution. So why would we talk about evolution in this public goods game? We've set it up in very kind of classical economic perspective. I even drew little green dollar bills. And that's not something that you expect to find in evolution, is it? Well, maybe not exactly that, but it is possible that you could have individuals who are genetically programmed to either make some kind of contribution to a public good or not make a contribution, and that contribution could be amplified if it is made. So the benefit is amplified. I'm not saying necessarily that it outweighs the cost, but depending on how it's distributed, it could. So maybe if I make some kind of contribution, there's a benefit that's bigger than the cost to me, and the only reason it's not a bigger benefit to me is because of the distribution. It gets shared around, and that's not unreasonable. There are natural systems that have exactly this kind of setup, and we'll talk about some of them in class, I expect. So to approach it from this perspective, we need a population with 2 types of individuals, and we'll need to keep track of what is the frequency of one of these types. Let's say X is the frequency or proportion of C types. And as we talked about before, with the evolutionary approach, the basic idea is that we sample individuals, have them play the game, and the payoffs that result become or contribute to their fitness. And their actual fitness is averaged over many iterations of doing this. So now we're going to sample not just pairs of individuals, but groups of n individuals. And as I said, the payoffs now are the fitness. So to figure out the fitness or the payoff of either type, we need to know how many others in the group are cooperators. So let's call that K bar. And we'll say that's on average, and that's what the bar means. So on average, how many others in the group are cooperators? Well, we can work that out. K bar, there are n-1 others in the group, and the probability of any one of them that we sample to be a cooperator is just X, the frequency of cooperators. So from that, we can work out the fitness of a defector, and that is just, as we said, the payoff to a defector if he or she has K bar cooperators in that group. So that's K times C times R divided by N, just like we did before. And the fitness for a cooperator is just the payoff for a cooperator on average. So if there are an average number of other cooperators in the group. And we already saw that was K plus 1 times C times R divided by N minus the cost this cooperator has to pay themselves. And now we substitute in N minus 1 times X for K bar. And we get X times n-1, and then a plus 1 for the extra cooperator, that's me, myself. Then we do the growth and the distribution, and remember that I also had to pay a cost C. And if we work through that, we'll see the same kind of thing as we saw for the economic case. That is that FC is equal to FD minus this factor, or this term, 1 minus R over N times C. So that's all we need to write down the replicator equation. So dx dt is equal to x times 1 minus x times fc minus fd. And fc minus fd is just the remainder, which is this term that we saw. So it's x times 1 minus x times this term, 1 minus r over n times c. So this whole thing here, it's less than 0 if r is less than n. On the other hand, it's bigger than 0 if r is bigger than n. So what happens in the dynamics here depends on how big r is. So let's draw this out. Let's draw the dynamics. And we'll want to do this for r is less than n and for r is bigger than n. So if r is less than n on the left-hand side of the graph, then this factor is negative. So that means that dx dt is negative everywhere in the range between x equals 0 and 1. You can check that for yourself using whatever method you like. We talked about a few in class. But basically what we're talking about is we're going to have a smile, an upward opening parabola. And on the other hand, if r is bigger than n, then it's positive everywhere. So we have a downward opening parabola. Now remember how you figure out the dynamics. If dx dt is negative, like it is here, that means x is decreasing over time. So we start at one value of x, and we wait a little while, and we have a smaller value for x, and a smaller value, and a smaller value. So we're tending towards the left. And because of that, we right away know that the equilibrium here is unstable, and the equilibrium here is stable. And the exact same reasoning applies, but things get turned around. On the other hand, if r is bigger than n, then dx dt is positive, which means x increases over time. And if it's increasing, then it's moving to a larger x, it's moving to the right, which means that 0 is unstable and 1 is stable. So there we have it. We know then that when r is less than n, then x decreases over time, and eventually it goes to 0. X is the frequency of cooperators, so we know that in this evolutionary setup, cooperators go extinct. On the other hand, when r is bigger than n, then the frequency of cooperators increases to 1, which just means the others, the defectors, go extinct. Let me just mention another interesting tidbit about all of this. Let's call it an aside. So we're going to talk about something called Simpson's paradox. So what we've seen here is that in each group, the defectors do better than the cooperators. And actually, I don't know if you've seen that exactly yet, but check it for yourself. So if there was, if I was a defector, let me write it like this, because if I was a defector and there were k cooperators in the group, then one of those cooperators would see an environment where their payoff was PC, but there would be k minus 1 other cooperators. And if you compare those two things, you'll see that the PD, the payoff for the defector in that scenario, is bigger than the payoff for the cooperator. And that's true even when R is bigger than N. But does that make sense? The defectors are doing better than cooperators when R is bigger than N? That kind of challenges our thinking here, because we saw that cooperators invade defectors, and the defectors go extinct when R is bigger than N. So what's going on? Well, this is exactly an instance of Simpson's paradox. And Simpson's paradox is a result seen in statistics, and it comes about when the result for an aggregate or an average of the population is different than the individual groups that compose that average. So if you want to learn more about that, it's quite interesting. Just look it up on Wikipedia and you'll see some interesting results and a demonstration there. You've probably seen it in a statistics course. And in this case, how that applies is that the cooperators, by just being cooperators themselves, are more likely to be in groups with more cooperators. And how does that work? On average, cooperators will see k-bar other cooperators plus themselves in a group, whereas defectors will just see k-bar. And we can see that right here, the plus 1. That is where that k-bar plus 1 comes in. And that's what makes FC bigger than FD when R is bigger than N. So when they're in the same group, then cooperators will be doing worse than defectors, but they're not always going to be in the same group. The next sampling will put cooperators and defectors into different groups, and on average, cooperators will be in groups with more cooperators because they're one of them. So that was just a little aside. That's kind of an interesting way of seeing things. So this leads into a big question in both in economics and evolution, and I want to approach it from the evolutionary angle, and that is the problem of cooperation. So let's look at the fitness at the equilibria, both the stable and the unstable one. So cooperators at equilibrium, if we're talking about cooperators, that means everybody has to be a cooperator. So when x equals 1, then the fitness of each of the cooperators in that group, let me write x equals 1 here, and I'll look at x equals 0 next. Okay, so the fitness of a cooperator when x equals 1. You can check it for yourself. It turns out to be just c times r minus 1. The fitness of a defector when x equals 0. Nobody is cooperating, nobody's contributing, the fitness is just 0. So again, like we saw with the economic situation, here, if r is bigger than 1, then let me call this fitness of any cooperator in a group of all cooperators, population of all cooperators, is bigger than the fitness of population of all defectors, or anyone in that population. So this is actually a kind of an evolutionary problem. When we're in the range of r being between 1 and n, cooperation is lost because x goes to 0, even though population of all C has a higher fitness than all D. So if we could create a utopian population of just cooperators, that population would have a really nice and high fitness. The problem is the presence of even one defector would break the system. What I'm saying here is, in this case, when R is less than N, this equilibrium is unstable, but it has a higher fitness for all its constituent members than this equilibrium. Evolution actually drives us away from the higher fitness. And that's kind of a deep concept in evolution, because what we're talking about here is a matter of what's good for the individual versus good for the group. And the individual, or technically the gene, wins every time. There maybe are a few caveats that or conditions on that, but I don't want to get into those. But the main message here is that it doesn't matter that the fitness for the group or the population is higher here. The presence of even one defector moves us away, and that defector has a higher fitness than even those cooperators do. So it spreads in that population. And as it spreads, the fitness of the whole group goes down, but the fitness of the defectors in that population is always higher than the fitness of the cooperators in the population. And so we get driven further and further to the left, and we end up in a population with all defectors that all have low fitness. So the problem is that selection can't support cooperation with the way we have things set up. So I could imagine that these kinds of situations really do arise. And an interesting question then is, how has evolution solved this problem? So how can cooperation evolve under these conditions? And part of the problem is we've got things like we've got just two types of individuals. Our groups are formed completely randomly. And these kinds of setups really all work against the formation of cooperation. So we need some other mechanisms in place. And if those mechanisms do happen to evolve, then they can really benefit the cooperators, and you can get cooperation evolving despite this kind of general framework. And this is an ongoing area of active research, both theoretically and empirically, in all sorts of natural populations. Okay, I think that's all I need to say, so let's just review what we did. We introduced the public goods game. We looked at the economic solution, and what we found there is that all defect is the Nash equilibrium in the case when R is less than N, but we saw that all C is mutually preferred when R is bigger than 1, which means that we have a social dilemma when both those conditions are true. Next, we looked at the evolutionary approach using the replicator equation, and there we saw that everybody defecting is a stable equilibrium when R is less than N, but all C would yield higher fitness when, again, the condition is R is bigger than 1. So we might call that an evolutionary dilemma when R is between 1 and N. And that is the problem of cooperation. Okay, that's all I've got for this lecture. Thanks for watching.